In this video, we're going to take a look at some graphs that enlighten. So in particular, we are going to look at graphs that are enlightening for quantitative data, right? So that's data that represents, that are numbers that represent counts or measurements. So the first type of graph that we have is a scatterplot. So a scatterplot, this will plot paired quantitative data on an X and Y axis. It's worthwhile. It will help you see correlation, see how those X and Y values, the paired values, how are they related? Does there appear to be some kind of relationship, right? And so what that looks like is you just have a bunch of dots that are representing the pairs of data, right? So those pairs, they could be like before and after measurements. They could be just two values that are naturally going together, right? So if you have a couple, you could look at some characteristic of one member in the couple and a characteristic of the other. You could have things like blood pressure in the left arm as compared to the right arm for the same person. So you have these values that are paired, and you plot that paired quantitative data. In business, you might have things like the amount of income compared to the amount of outflow. Right, so how much money is coming in compared to how much is going out. You could have the amount of profit compared to the amount that is spent on advertising to see if advertising appears to be effective. Right, so there's a variety of things that you might look at. But that's a scatterplot, so that's one way we can visually represent data that's numerical. We could also have a time series plot. For a time series plot, you plot quantitative data on an XY axis based on the time that it was collected. Right? So down here on the x-axis, you have the time, and then on the y-axis, you would have the value. So you could have like 12, 1, 2, 3, 4, and you just have your values at each of those times. So we can see how did those values change over time. Right? This happens naturally when you look at stock market kinds of things. If you are trying to track the growth of like a virus, so how many new people are obtaining that virus each day, this time series graph is used in a variety of places. But that's another way we can represent quantitative data. We might use a dot plot. So dot plot, that puts dots above corresponding data values on a number line. It gives you a quick idea of a frequency histogram. Okay, so if we had, say, 7 here, and the value 7 was observed twice, we would put not 1 dot, but 2 dots above 7. And maybe 8 was not observed at all. Maybe 9 was observed once, we put 1 dot above it. 10, maybe that was observed once. No observation for 11. Maybe 12 was observed not twice, but maybe 12 was observed 3 times. Maybe 13 was observed 3 times. That sounds like bad news. 14 maybe was observed once, right? So here we can look at this. This gives us a quick idea of a frequency histogram. You can imagine putting bars here. So these aren't part of the dot plot, but you can kind of see how that looks here. You can see the heights based on the heights for the different values, the number of dots that we see there. Right? The next type of distribution that we have is a stem plot. It's also sometimes called a stem and leaf plot. Each leaf is usually the rightmost digit, so that's for the leaf. It's usually the rightmost digit. The stem is then often anything to the left of that leaf. Now here you do want to have each of your data values to have the same number of digits, to end at the same digit, I suppose is the better way to say it. You want them to end at the same digit. So if most of your data values go to a tenth and one of your data value goes to a whole number, then that whole number data value, write it as 0.0, so it goes to tenths. If most of your data values are whole numbers and one of them goes to a tenth, then you might round that data value because it makes more sense to look at the whole number part. You put the distinct stems in a vertical column in increasing order, and then you place all leaves associated with the stem next to it, also in increasing order. So in some of the previous videos, we looked at a hot dog data set. Let's look back to the frequency distribution we created for our hot dog data set. So here was that frequency distribution we created for our hot dog data set. Let me go back to the data set itself. And so for our hot dog data itself, here is our hot dog data. Our smallest number of calories that we had was 111, right here. That's our 111. And so I'm going to use a stem of 1,1, and then that will have a leaf of 1. All right, so 111 occurs one time. There were no other values that started with 1,1. So the next stem that we would have is 1,2. Now I jotted down 1,2. If you look through this data set carefully, you will see that there's not any values that are in the 120s. And so there's not going to be any leaves on that stem. Then we have our 130s. We have multiple values in the 130s. So we have a 131 right here. We have a 132. We have a 139. So we're going to have leaves that are, we have a 135. So we're going to have leaves that are 1, 2, 5, and 9. Associated with a stem of 13, right? So that 13 is representing 130, and then, so this is representing 130, 131, and we have 132, we have 135, and 139. For the 140s, we have 141. We have a 149, so 1 and 9 are both leaves. We have a second 149. We're going to use that twice, so we have 141, 149, and 149. So our leaves are going to be 1, 9, 9, and there's a 148. So 1899. So even though there were two values there, we are going to write each of those leaves distinctly separated. In the 150s, we have 152, 153, 157, so 237, and 8, 158, 237, 8. Our 150s. So we had 152, 153, 157, and 158. In the 160s, we have maybe nothing. Nothing in the 160s. In the 170s, we do have a 176. We have a 175. So 5 and 6 in the 170s. In the 180s, we have 181, 184, 186, 1, 4, and 6. That looks right. And then finally, in the 190s, we had 190 showing up twice. So 190, 190. The only value we see that we didn't star was that 111. That was the first value. I just put the star over here to the left. So we did write that. Perfect. So that over here, this is our stem chart or stem plot. This also gives us a sense of a frequency distribution. So it looks like a frequency distribution on its side, a frequency histogram on its side, rather. So in the 110s, we have one value. So these bars are not actually part of this distribution. But you should be able to look at it and imagine those and have a quick sense of what that distribution might look like. All right, so it just looks like this frequency distribution on its side based on those links. Two other kinds of charts that will help us to represent numerical data are frequency polygons. Here for frequency polygons, you have dots are placed above class midpoints at a height corresponding to the frequency of the class. We connect the origin to the first dot, and the last dot gets connected back to the x-axis of what would be the next class midpoint. So that's a frequency polygon. It's like a line graph, but it has these other couple items that are associated with it, connecting back to the origin, back to the axis. An ogive is a line graph for cumulative frequencies. So instead of putting dots at the frequency, you put a dot at the cumulative frequency. So your lines should be flat lines, or they should go up because you're adding more. You should never be taking away things as you go cumulatively. Here, typically you would use class boundaries here. All right, in the next video, we'll take a look at graphs that are worthwhile for qualitative data. We'll see you there.